Mathis. I'm Scott Arnold, Senior Manager of Publications and Standards for Air Movement and Control Association International. On behalf of our more than 400 members worldwide, I want to thank you for joining us. We realize there's a lot to see and do at the AHR Expo. We respect and value your time and hope you find this educational session worth your while. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. This session is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. And with that out of the way, let's meet our presenter. James Mathis joined the New York Blower Company in 2016, shortly after graduating from the University of Illinois at Chicago with a bachelor's degree in marketing. He started in the technical support group, gaining broad knowledge of the company's products and working on special pricing for custom catalog quotes. In 2019, he moved into project management, overseeing complex projects often heavily specified to applications such as API, sanitary, and wastewater treatment. He moved into his current role of OEM sales manager in 2023. James?
Thank you, Scott. And good afternoon, everybody. And thank you for coming today. It's great to see such an awesome turnout. Today's going to be a pretty broad overview of a lot of different fan fundamental topics. And so with that, I'm going to jump right in. The purpose of this presentation is to educate you industry professionals on fan selection methods. And so we're going to go through fan types, selection practices, and fan performance. And by the end of this presentation, our goal is for all of you to be able to understand fan laws, at least the three that we're going to look at today, and apply them to understand how they affect fan performance. We're going to look at best principles when selecting a fan. We're going to look at different types of fans, different types of fan wheels, and why you might select one over another for a given application. We're going to compare flow control methods and understand how they're used in the field. And we're going to look at non-standard air to understand how it affects a fan's performance and its selection. We're going to start with some key terms. CFM stands for cubic feet per minute. And in the context of a fan, it quantifies the amount of airflow or the volume of airflow that a fan is moving. CFM is just one of several ways to quantify airflow. SP stands for static pressure. Again, often quantified in inches of water gauge, but that's just one of a few ways to do it. And static pressure is really resistance specific to a system, to a fan's airflow that is trying to move through the system. And every system has its own unique amount of resistance to airflow, and it's based on pressure loss, things like elbows, short duct runs versus long duct runs, dampers, silencers, all these create pressure loss specific to that system, and a fan has to overcome it by generating that much pressure to be able to deliver the airflow that's needed. RPM is revolutions per minute. That's the speed, typically the fan speed or the driver that's running it. And BHP is brake horsepower. That's a way to quantify the amount of energy the fan consumes when running at a given operating point. So we're going to go over three of several fan laws today. And fan laws look at the relationship between one aspect of a fan's performance and another, and how changing one affects a change in another. So when you're looking at fan speed, it can have a change on fan flow, fan pressure, and fan horsepower consumption. And we're going to look at the first fan law right now, which compares the relationship between speed and flow. And it happens to be a one-to-one relationship. And a good way to conceptualize this is to think of the wheel and the blades on a wheel as a set of equally sized shovels, each moving an equal sized amount of volume as they rotate. And so with that approach, it would stand to reason that if you increase the frequency with which each equal sized shovel or blade is moving an equal sized amount of volume or matter, it has a one-to-one relationship. And mathematically, that's the change in CFM or CFM new over CFM old is equal to the change of speed or RPM new over RPM old. So we're going to start with an example for an operating point. On the left column, you have an operating point of a fan that's moving 10,000 CFM while generating 10 inches of static pressure. It has to move at 1,000 RPM to do that, and it consumes 100 brake horsepower to do all that work. And on the right side, we're going to look at how those capacities change by doubling the speed from 1,000 to 2,000 RPM. And we know from the first fan law that you're going to also be doubling CFM in that case from 10,000 to 20,000 CFM, a one-to-one relationship. Now, static pressure is more sensitive to a change in speed. It varies as a function of the change in speed squared. And so we started with 10 inches of static pressure in our original capacities. And so X over 10 is equal to the change in speed, which is 2, because we've doubled it, 2 squared is 4, and so the equation is x over 10 equals 4, which solves for 40 inches of static pressure. You've quadrupled the amount of pressure by doubling the amount of speed. Now, brake horsepower is again the same setup, but now the brake horsepower varies as a function of the speed cubed. So it's extremely sensitive to a change in speed, with the idea being when you're selecting a fan or dealing with a performance deficiency in the field, you have to understand the headroom that you have on the motor that the fan's running on to see if you even can change the speed. And typically, if you have a fan that's going to consume 28 brake horsepower, if you're selecting a 30 brake horsepower, you're really gambling on the system resistance that you are giving being exactly right. If there's a little bit more, then it's going to either be at a deficiency and not be able to overcome the system resistance, not be able to deliver the airflow, or you'll be in a situation where you have to speed it up, and the amount of headroom you have on the motor will determine how much you can do. So brake horsepower, we started with 100 brake horsepower, and x over 100 is going to be equal to the change in speed, 2, cubed, which is 8, which solves for 800 brake horsepower by doubling the speed. Now, doubling the speed is a pretty extreme example, but that gives you an idea for what you need to watch out for in selections and in the field. So there are a lot of fan selection considerations. Don't worry, I would never read this many bullet points to a group of people, but we're going to go over the high-level ideas as we go through this. The idea where you want to start is what the fan needs to do. How much flow does it need to move, and how much pressure does it need to generate? And there are going to be multiple fans that can do that, multiple sizes and multiple types of fans. And depending on what's moving through the airstream, or whether you're valuing burst cost versus overall owning cost of a fan, is going to determine what you want to do. Sometimes using the smallest, fastest fan is going to be the cheapest upfront option, but it might consume more energy than buying something a little bit bigger that runs a little bit slower. It's a bigger, heavier wheel, but running it slower is a big deal. Speed is a killer for brake horsepower consumption. That's the third fan law. And aside from the pressure and flow, you have to think about how much that air weighs, or the density. And the standard density is defined as standard air conditions, which is 70 degrees Fahrenheit. It's 0 feet above sea level. And that changes with variables like altitude, temperature, and airstream composition. So we'll get into that a little bit later. But aside from what the air weighs, you have to think about what it's made of to see what decisions that drives about what kind of fan makes sense. Is it a clean air that's going through the fan, or is it dirty air, which can describe whether you want to look at a backward inclined fan or a radial bladed fan. Today we're going to focus mostly on backward inclined fans because in the AHR industries, that's really the more applicable player. If you're dealing with explosive or flammable gases or materials in the airstream, there are different levels of spark resistant construction you can consider. Basically constructing parts of the fan out of non-ferrous components, 5% or less of iron, so that it's designed not to spark if it's dealing with something that could catch fire. If you're dealing with corrosives, then at the minimum, you would want to look at some kind of a coating system, which can be as sophisticated as you need it to be. But if you need to take a further measure to protect a corrodable material from paint, then you can look at something like corrosion resistance, which would be aluminum or stainless steel. There's a lot of other exotic alloys depending on what temperature or speed that it's running at. And then elevated airstream temperatures. Material have derates at higher temperatures. And so you might be able to hit an operating point at a lower temperature with a carbon steel wheel. To do that at a faster speed at a higher temperature, you might need to go to something like a stainless steel or a xenon, some kind of exotic metal that has a lower D-rate at a higher temperature. Some other fan selection considerations are general ideas of what's going through the airstream to put you into the kind of fan that makes the most sense. So if you're dealing with small amounts of dust or smoke or a completely clean airstream, then you're looking at backward inclined fans or axial fans. It's really the most efficient, lowest energy way to move air that's clean or relatively clean. If you're dealing with light dust, smoke, or moisture loading, there's still some kinds of backward inclined fans that could do that, some that can't. And then radial bladed fans are great for that application. If you're dealing with high particulate loading, heavy material, then really radial bladed fans are the only thing that are made to do that. But at the cost of the efficiency, which we'll look at a little bit. So fan noise is a big topic, especially in more commercial or residential applications. You're dealing with a lot of neighbors and a lot of noise concerns. And fans can be noisy, and they vary with a lot of things like the size of the fan, how fast it's running, how efficient it is, the amount of flow or pressure that it's moving, and mechanical stuff like vibration and turbulence in the airstream, that all affects the amount of noise that it's going to be made. And AMCA 300 describes how you should test a fan in a laboratory setting for sound. And you can go another step and find a fan that's rated to AMCA 311, which says we've tested the fan to the AMCA 300 standard, but then we've certified it to AMCA 311, meaning that we have submitted our fan to AMCA. They've tested it in their lab to make sure that it agrees with our sound levels within a small tolerance, and then they're going to check that and maintain it. So it's another degree of protection to make sure that the sound that you're buying is what it's going to be in the field. And something to note is that that's really specific to what the fan does. You have to also think about what the installation conditions are going to do to that fan. Or is it surrounded by a lot of metal objects that are going to create a lot of resonance? So something to think about to stay out of trouble with noise. Now, drive configurations have a few different options. Really, you're looking at direct drive or belt drive. And when you're dealing with a direct drive, the fan wheel and the motor shaft are directly coupled one way or another. So they're running at the same speed, either the nominal motor speed if you're doing direct online, or if you have a variable frequency drive, then you're able to run the motor and the fan at something other than the nameplate speed. So two major direct drive examples. On the top right, you have an arrangement 8 fan. This is where the wheel and the motor shaft are coupled with a set of shaft and bearings. And what this does is you don't have the motor shaft directly in the airstream and limit it to things like temperature or corrosion. Arrangement 4, much smaller assembly, more compact, lower footprint, smaller upfront cost, but you have a motor shaft directly in the airstream and you're limited to what that can handle. The motor bearings are so close to it at that point, if it's a hot airstream, you're really limited to about 150 degrees. If it's a corrosive airstream, then you're dealing with a custom motor to get something like stainless steel, which skyrockets the price and the lead time. But if you separate that motor from the airstream with an arrangement 8, you're dealing with a higher upfront cost, but now you're only limited to what the wheel is made out of. And the fan manufacturer can be really flexible with what they make the wheel out of, how thick it is, what material it's made out of to handle pretty much whatever it needs to handle. Now with belt drives, you have flexibility because the fan wheel is running at a different speed than the motor shaft. And that's done with a set of pulleys essentially. You've got belts and shivs or pulleys. And that drive ratio is the difference between the two. It's the motor RPM divided by the desired fan RPM that gives you the drive ratio of how to select those shivs. So two major examples of belt drives. You have the arrangement 1, which is again your bigger footprint that gives you more flexibility with the motor you use, because these are going to be typically mounted on a unitary base that the fan manufacturer provides. Some people will mount them directly to concrete in the field. But the idea is you can make that base or that footprint as large as you need to accommodate a very large motor or a very heavy motor. So you have a little more flexibility with that, but at the cost of a higher upfront cost and a bigger footprint, as opposed to the arrangement 9, where you have the motor tucked up on the side of the pedestal. But now it's limited to the heat in the fan housing that might be radiating and is very close to the end bell of that motor, the cooling fan. And you also have to deal with the weight restrictions on the rails that motor is sitting on. And separate from the physical drive configuration of the fan, you can also think about the installation configuration. How is that fan going to be installed in the field? And the idea here is that the fan performance that you're buying, that you see rated in a fan curve or in a catalog, is based on ideal testing configurations, which is good because it gives a baseline to fan manufacturers to test their fans so you can compare them to one another. But you have to think about the losses that come in with the ducting and how you change that performance in the field. And inlet conditions is a big part of that. And you can really have a straight run of duct into the fan's inlet, or you can have a 90-degree really close to the inlet. And first, if you look at the top left and the top middle, these fans are pulling off of dust collectors. These are on the clean side, pulling negative pressure off of it. And it drops straight down into an elbow before you get a straight run of ductwork into the inlet. So the idea here is, since air has mass and weight, as it comes down that elbow, it's going to ride the bottom of the elbow and it's going to load it unevenly. And then when it comes out, it's going to tend to load the bottom of that duct, and it takes a certain amount of distance to straighten that air out. So you want a good amount of distance running into the fan inlet. If you can have a straight run, that's great. And you want it to be multiple times the diameter of the inlet. There are more rules on that get into system effect. And another guy from New York Blower is going to be presenting on that tomorrow, Jim Conway. Another method is to look at the top right and the bottom middle. This is a much more compact option where you drop the ducting directly into the fan's inlet, and it makes a 90-degree at the inlet. And all of these are going to have losses associated with them, but the beauty of an inlet box is that you're going to buy it from the fan manufacturer who has testing data on it, and they can tell you what that D rate is going to be. You could look at their selection software and add an inlet box, and it will tell you what the pressure drop is. Or you could lock the pressure, and it will increase the speed so that it could overcome the loss associated with the presence of that inlet box. Now, separate from the installation, there are different methods of flow control to think about. And there are different reasons that you might need to alter the amount of flow that a fan is moving. It might be because you're anticipating a future plant expansion. The fan's going to do one thing today, but you're going to increase that and stop throttling back the fan performance tomorrow. Or you might have different varying capacities throughout the day of a fan. Maybe you need to do one thing for a certain cycle of your system and one thing for another thing in your process. But one way or another, if you need to control flow, there are different ways to do it. There are different kinds of dampers to think about. There's speed control via variable frequency drive. And then there's also variable pitch blades if you're dealing with certain kinds of axial fans. So starting with dampers, these are typically installed right at the fan outlet or at the inlet of a fan or at the inlet of an inlet box. And we'll look at the differences between these. Starting with outlet dampers, as you close these off, you're adding back pressure to the fan and limiting the airflow, just like the floor vents in your house for your residential HVAC setup. This is throttling back the flow. But by the time the fan's air has gotten out of the outlet, the fan has kind of already done its work, everything that it was designed for. And so you're really simulating more resistance in the system. We talked about how the give and take between pressure and flow. As you close those blades off, you're adding pressure and reducing airflow. On the top right, you have a parallel blade damper. The blades open parallel to one another, as opposed to the opposed blade damper that kind of mirror each other. And the difference is the amount of modulation that you get in airflow. The parallel blade damper is going to make more significant swings in airflow than the opposed blade. So that was a flanged external outlet damper. You also have the option for internal, if it's a little more compact. That's a little more light duty now that it's built into the fan, less moving parts though. And then you also have the variable inlet vane damper. So the variable inlet vane damper works very differently from the outlet damper. How it works is it has these vanes that you close, and as you close them, it creates what's called a pre-spin or a vortex. So the air is about to be moving in a direction when the wheel gets a hold of it, and this pre-spins it in that direction, which diminishes pressure, flow, horsepower consumption. The fan could even run quieter. So it acts a lot like reducing the speed of a fan, but it looks differently on the curve. I'll show you that in a minute. You compare that to an inlet box damper. This is mounted at the inlet of an inlet box, and you might notice that's exactly what we were looking at with the parallel blade damper on the outlet. But aside from the size, that's the exact same design concept. But when you put it on the inlet of an inlet box, it does the same thing as a variable inlet vane damper. It creates a pre-spin that reduces flow, pressure, and horsepower consumption. Now, I mentioned variable pitch blades on certain kinds of axial. So there are fixed pitch axial fans and adjustable pitch axial fans. But the idea is, as you adjust the blade angle to be more parallel with the direction of airflow or axially through an axial fan, it's going to increase the amount of pressure it generates, the amount of flow that it can move, but also increase the amounts of power that it takes to do that, and it decreases the efficiency that it can do the work at. That can be done either manually by popping the cover off like in the top, accessing the nuts, loosening them, and then adjusting the blades equally to one another using some kind of a blade template that you would buy from the fan manufacturer. Or some people design them to be done automatically in flight or in operation, where that can be done with hydraulics or pneumatics. And speed control is an increasingly popular way to change flow. It's very intuitive, and VFDs are becoming more and more common because they're more user-friendly, they're more affordable, they're more compact than they used to be, and all over the AHR show, you'll see very small drives built into motors on EC motors. Electrically commutating motors are getting more and more common in the industry. There's an increasing demand for them. And if you're dealing with a smaller motor, about 15 to 20 horsepower, it's a very good compact option to be built into a motor. Now, when you use any of these different flow control methods, it does a different thing to the fan curve. And we're going to focus on the top set of curves. And on the top left, we have the outlet damper curve. And I mentioned when you close off the outlet damper, you're really changing the system. You're simulating more resistance in the system. The fan has already done its work. It's left the outlet. And so as you change those outlet damper blades, you have in this case, three separate system curves intersecting one single fan curve. And the three system curves represent different outlet damper open and closed positions. As opposed to the inlet vane or inlet box damper, where when you close that, it kind of acts like changing a fan's speed. So now you are changing the fan characteristics because you're changing the inlet condition. So now you're changing the way it's been tested, and you've got one single system curve being intersected by multiple fan curves represented by different inlet damper configurations. But you see that they're joined and kind of umbrella out at the top. It's because this is still the same fan, but you're altering the way that it works on the air from the inlet. And then speed control, you can see the difference. Even though it really has the same results as inlet vane damper control, it does an umbrella at the top because now you're creating a new fan curve for each speed that fan's running at. Similar arc and shape to the curve because it's the same fan, but every time you increase the fan speed, that curve shifts out, and every time you decrease the speed, the curve shifts inward. Now getting into centrifugal fan types, there are really a lot of types that you could look at. There are radials, pressure blowers, backward inclines. You could look at axial fans that have different types, but today we're just going to focus on backward inclined fans. So two very common types, you have the backward inclined single thickness blade and the backward inclined airfoil blade. There's also a backward curved option. But the single thickness can handle some amount of moisture in material because it's fairly simple. It's a rectangular piece of steel as opposed to the airfoil where it is hollow. So there's going to be moisture buildup that it's susceptible to. It's susceptible to abrasion and material eating through it. This slide is labeled wrong, but this is a PLR or a single thickness wheel where you can see the weld marks to show the backward inclined orientation as opposed to the airfoil with the hollow inside. And you can see how when this is misapplied, the abrasion could eat right through the material of the blade. That wear pattern exposes the hollow interior of this. So when you look into the outlet of a backward inclined fan, you've got about 50% of the casing taken up by the wheel width. And the other 50% is taken up by the inlet cone. And the idea here is that there's a lot of dead space in a backward inclined fan, which is a characteristic of a high flow fan. Backward inclined fans move high amounts of airflow at lower amounts of pressure. And they do it as efficiently as possible. And since I have 30 minutes longer than I realized, which makes a lot more sense, let's start from the beginning of this category. The most efficient way to move a lot of air with a centrifugal fan is a backward inclined fan. They're quiet, they move air using low energy, but they don't consume a lot of pressure, or they don't generate a lot of pressure. When you're looking at a fan curve, a couple of things to be aware of. The static pressure curve has a peak where it drops off. And at that peak and to the left of it is an unstable region. It's called the stall region. And you want to select a fan about 5%, 10% to the right of that. You don't want to select it way to the right of it because that's not really where fans were designed to run. It's not going to be an efficient point of operation for it. But if you select it 5% or 10% to the right, you're going to be in a good spot for a backward inclined fan. What stall looks like when it's extreme, if you were to take an inspection port off the inlet upstream of it and put like a plastic wrapper, you would see it pulling into the fan and pulling out. And that's because the fan's kind of breathing. It's not supposed to. It's supposed to go into the inlet and out of the outlet. So when the fan is in a surge or in a stall, that's the most extreme case, if not very unstable flow conditions. And it's kind of an interaction between the fan and the system that it's installed in. It also has a non-overloading horsepower characteristic. So what this is where the green horsepower curve peaks and starts dropping off further to the right of the curve. That's a non-overloading horsepower characteristic, meaning as you get closer and closer to the full open point of the fan curve, you're not necessarily generating more power because you have pressure dropping off as you get to that higher airflow part of the curve as well. So when you're dealing with an inlet cone, this is something that is on every single backward inclined fan. It's the way that those wheels were designed to work on air, is by having the air funneled through a cone or a venturi shape into the center of the wheel. And the installation of that cone and how it marries up to the wheel is critical for a fan's performance. So this is an idea of what a good inlet cone installation looks like. You've got the inlet cone meeting right at the lip of that inlet shroud, and it's loading the entire width of the blade. On the left, you have an inlet cone that's protruding too far in through the wheel's inlet shroud. And you can see you're not utilizing the full width of the blade. And so you're going to have pressure loss associated with this, and it's not going to operate as efficiently. As opposed to the right side, where you have an inlet cone that's not going far enough into the inlet shroud, that's going to create a draw of recirculation of air around the wheel. So it's still going to move air in through the inlet and out through the outlet, but it's not going to be able to create the amount of pressure that it was supposed to. It's going to be a little more turbulent. So we just looked at different kinds of backward inclined fans installed in a traditional housing or a volute shape or a scroll. You can also put these in other kinds of configurations. This is a very popular one, especially in our OEM segment, where you put that wheel on a plug and you can insulate that plug as much as you need to, as thickly as you need to control extreme temperatures. These are typically used in ovens, freezers, coolers, dryers. And the idea is if you separate that wheel from the more sensitive components like the belts, the bearings, the motor, then you can only worry about the wheel construction and the speed and the temperature that can handle. Another variation of a backward incline is a double width, double inlet fan. So this is the same kind of fan we were just looking at. It could be a single thickness or an airfoil wheel. But if you put them together on a common center plate, it doubles the amount of airflow that it can move. And that's holding the diameter and the speed equal. And that's because a wheel's width is responsible for the amount of volume that it can move, but the diameter of a wheel is responsible for the amount of pressure that it can generate. And you'll notice if you look at the blades, they're staggered between these two separate wheels. And that has to do with blade pass frequency. So if you have a wheel rotating past this cutoff sheet above the inlet cone, that's there to stop recirculation of air. That air has mass and it has a tendency to rotate through the housing, and you have to interrupt that with a cutoff sheet, and that's what's welded there to the housing that's kind of blocking the view of the cone. So as that wheel passes through that cutoff sheet, there's turbulence associated with it. It's vibration, really. It's aerodynamic, and it's a lot like when you stand by the L in a subway. When you have the train cars passing you individually, you can hear that frequency associated with it. The same thing happens each time the blade passes a cutoff sheet. It's called a blade pass frequency. And if you offset the blades, then it decreases the magnitude of that blade pass frequency. That's why you don't see them lining up on these types of fans. But since it's a double width, double inlet fan, you've got an inlet on both sides. One of them is going to be designated on the drive side, but that means you've got bearings in the airstream unless you somehow extend them out of the ductwork. One example is inlet boxes. If you have inlet boxes on both of those inlets to drop the ducting down, then you could extend the shafting out and have the bearings mounted externally. An example of a backward incline installation, you've got a lot of accessories here to think about. You've got ducting dropping down into an inlet box. Again, best way to do a 90-degree turn at the fan inlet. And then as it exits the outlet, you have an outlet blade damper. And then that goes through a transition from rectangular to round into a 90-degree elbow. And then at the very top left, you'll notice that larger diameter that indicates a silencer there. So there's some pressure loss associated with that inlet box, that damper, that elbow, and that silencer. And that all can be calculated. There are ways that you could adjust for it. And there are some ANCO standards I'll point you toward at the end that'll help with that. Now the radial tip fan is kind of a hybrid of a backward inclined fan and a radial fan. It's meant for kind of the intermediate points. So I'm not going to cover radial bladed fans today because they're not as applicable to this industry, but they generate a lot more pressure than you would typically see in typical AHR type industries. And they move a lot more material than is really typical to AHR industries. If I have time at the end, I'll go through some of them. But the idea is with fan construction, the things you do to a wheel to make it able to generate a lot of pressure and handle a lot of material and really take the abuse of a dirty airstream, they all make it less efficient. And it's no fault of the design. It's really just the geometry that it takes, the gussets and the things that just aren't very aerodynamically friendly, but they're very rugged and robust. As opposed to the things you do to make a fan very efficient. You make a lot of curved blades, you make them hollow, you add a lot of shrouds. Really what it does is it adds moisture points and corrosion susceptibility. And it adds hang-ups. When you add shrouds to a wheel, it makes it more efficient, but now you've got points of hang-up for strand-type materials. So a radial tip fan is more like a backward inclined fan in the sense that it can handle some amount of light material, light dust. And it's called a hybrid because if you look at the 9 o'clock degree, or the 9 o'clock picture, it's got a blade that has a backward incline a lot like a backward curved wheel or backward inclined wheel. But if you look at the 1 o'clock picture, you see where that backward incline changes direction to a radial tip. And so the backward incline is where it gets its flow capabilities, but that radial tip is where it gets the higher pressure. And so this is for intermediate operating points that might be higher pressure than a backward incline fan could hit, but also higher airflow that a radial fan could typically hit. Now, forward curve fans are also another popular one in these kinds of industries. You see them in a lot of HVAC applications. Almost everybody's furnaces use these, and they're used in a lot of replacement air or makeup air applications. So the idea with these, you'll see all these blades, and these rotate and cup the air as they rotate. So they're moving a ton of air at a relatively low speed for the work that they're doing. And the significance of that is that these are common in hotter airstreams. You see these in dryers, blow dryers use a lot of these, car heaters use a lot of these, makeup air. And when you're dealing with hotter air, you have to either have a fan that can handle that temperature and the D rate at a higher speed, or you have to find a way to design it where it can run slower while moving all the air. And that's where you get all of these blades with a forward curved cup to them. You can move a lot of air at a slow speed. They're not at all used for material handling. They're clean air fans. You can tell by the construction. These are used to be light. They need to consume low horsepower, so they make economical sense. They're riveted often with lighter gauge construction, but they're great for clean air applications that are a little bit hot. A really common one is makeup air. If you've ever gone to a restaurant or some kind of a building and you can't open the door without resistance, it's because that building is under negative pressure or vacuum. That means they're exhausting air from the building. They're not making it up. They're not replacing it. And so makeup air units are the solution to that. You have air leaving the building, but you're returning that air back to the building. So this is a tubular centrifugal fan. This is another one of those alternate options for a backward inclined fan. And this puts a backward inclined centrifugal wheel, so it's moving air like this, into a housing that forces it forward. So it's kind of an axial backward inclined hybrid. And at first, that might seem a little counterintuitive. You've got a wheel moving air centrifugally, which means it's throwing it into the walls of this tube, but it has no choice but to go forward. And so there are losses associated with that, which is why you'll always see straightening vanes on these, because you're going to have chaotic airflow from that kind of counterintuitive way to move air, and you have to find a way to straighten it. And with those and the inlet cone, again, that's common to every single backward inclined fan. Even if it's on an axial fan, it's going to have that cone. And that's what allows this to be an efficient way to move a lot of air at lower pressures in a very compact ductwork application. And then you have the more traditional axial fans. This one is specifically a vane axial, which we'll look at more in a little bit. But axial fans get their name because they're moving air axially. They're moving in a straight line. And these blades are the ones that I mentioned. They can be fixed. They can be adjustable. This one, you might notice the blades are welded to the hub. That indicates this is a fixed pitch vane axial bladed fan. These are used for high flow and very low pressures and only clean air, a lot of general ventilation purposes. And then you have the non-ducted axial fans. This is more of a common propeller fan, something that would typically be installed in a wall, sometimes the outside of a wall. You see them in a lot of agricultural type buildings. And then you have a more cost-effective axial fan. This would be more of a duct fan. And you notice you no longer have those cast airfoil-shaped axial blades like we had in the first picture. Those are the same airfoil profiles that you would use in a backward inclined airfoil blade. You take that away and make it a little simpler. This is a more cost-effective way to move general clean air. You see these used on a lot of paint booth exhaust and general ventilation. And then you have the vane axial fan. These are more high-pressure solutions to move a lot of air. They're still relatively low-pressure, clean fans, but this is a little more of a robust way to do it. These are going to have straightening vanes on it as opposed to the duct fan. And you'll see the ratio of that hub diameter to the blade diameter. And that has to do with the amount of pressure that it can generate versus the amount of airflow. So holding the speed and the overall diameter of the wheel the same, the larger the hub is, the more pressure it generates. The smaller it is and the longer the blades are in turn, the more airflow that it can move. And they have very tight clearances. So often you're going to see it in an 1/8 inch clearance. Some people get down to a 1/16. And so there's a lot of art in the fabrication of these. Some people will buy the blade castings oversized and machine them down per job to make sure that they fit with the clearance they need. Because you have to keep a very tight clearance with these to get the performance that they're designed for. Very common axial fan application. This is on a gas liquidation facility where they don't need a lot of pressure. They need a ton of air to create the combustion that they need for their stack when they're exhausting. Another is in a grain dryer application. In this case, you have multiple axial fans stacked, blowing ambient air through heaters into these baffles. So as grain falls down through them, it's drying the grain. Another application where you don't need a lot of pressure, you just need a ton of air. Now, I talked a little bit about density earlier, and density is really the weight of the air. And there are several things that affect it, but you have to understand it so you know that the fan is running as fast as it needs to do the operation and the work that is prescribed, and also to understand the power consumption that's actually going to be consumed. If you have a fan selected at standard conditions, which again is 0.075 pounds per square foot, that's going to be very undersized or oversized depending on what the actual density is on site. One example is heat. It's 600 degrees Fahrenheit. Air is half the weight of standard air. Now, that's a pretty extreme example, but it's something to be aware of when you're thinking about a hotter application versus an application in just a high altitude area. So 18,000 feet, again, it's a pretty extreme example. It's a fan installed on top of a mountain, but you're dealing with density that's half that of standard air at 18,000. And then rarefication. It's extreme suction at the inlet of a fan. If you're dealing with something like 204 inches of vacuum at the wheels, at the inlet of that fan, that air thins to half the density of the standard air conditions. And then you have cold starts to think about. And this really gets into sizing the motor for your fan, if not using flow control. It really needs to be one of the two, because it's not always practical to size a motor so big that it can do the work that's needed of it, both in normal operating temperature and in a cold start. For instance, if you have a process where that fan is handling slightly heated air, but then that process has to come up to temperature over the course of 2 or 3 hours, then you're gonna have a condition where that wheel is moving full air at full speed if you're dealing with direct online, and you have to find a way to deal with that. One way is speed control, where if you're dealing with colder air, you slowly ramp up the speed of that fan so that it's not overamping the motor until the process comes up to temperature. And another method is inlet dampers, variable inlet vanes or inlet box dampers. You close them off to maybe 15% open so that you're throttling back the amount of performance it's doing so you're not overloading that motor until the process comes up to temperature, then you can slowly open it up. I also talked about spark resistant construction. So this deals with flammable or explosive airstreams. And AMCA, the Air Movement and Control Association, has defined 3 different tiers of spark-resistant construction. And the first would be the most extreme. That's where the entire airstream, AMCA-A, is designed of spark-resistant material. That's the housing, the wheel, the shaft, everything that the air touches is going to be spark-resistant. So that would be for an application where it's very likely that your application is pretty flammable. And if there was to create a spark, then you need the fan to be able to control it. As opposed to AMCA-B, that's what this picture is showing, where it's only a wheel and a buffer adjacent to the wheel that are non-ferrous. Other than that, there are a couple of provisions to stop the likelihood of the shaft and the wheel assembly moving, so it won't rub against any of the ferrous casing sides. And then AMCA-C is buffer construction. So that means that the wheel is not constructed of a non-sparking material, but there are spark-resistant buffers welded to the casing, or if it has an inlet cone like this one, typically aluminum, the inlet cone will be made out of aluminum, or if it's a radial bladed fan that doesn't use an inlet cone, you'll have a copper or a brass buffer welded to it. But the idea is these are different levels based on how likely it is that you might have something flammable in the airstream. And then corrosion resistance, another kind of non-standard air to think about. I mentioned different alloys. There's also FRP as an option. Very common in wastewater treatment where you've got all kinds of chloric acids and things going through the airstream to either treat the foul air or the foul air itself that can be very corrosive. Stainless steel is sometimes acceptable, but the extreme of that would be FRP. It's fiberglass reinforced plastic, which is basically a lot of chopped fiberglass resined up to create a smooth airstream. So that's the most corrosion resistant option before you start going to some of the alloys that are a little bit more cost effective. Aluminum, stainless steel, a lot of other exotics. Okay, getting closer to the end, we have a fan selection software on our website. This is available to everybody. So if you're sizing a fan, this is pretty user friendly for a way to do it. And it starts by entering the capacities we talk about. You enter in what you know about the fan. If you have specifics, if you want to cap it at a certain size or a certain speed, you can do that. You could enter in what you know about the temperature and the altitude, and then this has a density calculator. So you can hit that calculator button and enter in what you know about it, and it will tell you what the density is. And there are other calculators online for that kind of stuff as well. And once you enter in all your inputs, it's going to take you to all the different options. So I mentioned, aside from the capacities, there are going to be a lot of different kinds of fans that can do that. And it really comes down to what's the airstream made of? Or are we looking at the biggest, slowest fan that consumes the lowest energy? Or are we looking at the smallest, cheapest fan that's going to run faster and maybe consume more energy? Once you pick the one you're interested in, it'll take you to a page where you can get sound data, you could print air performance curves, and you can go deeper into the sound data, understand the housing radiated noise versus the inlet sound levels, the outlet sound levels, which you could deal with in different ways. High inlet sound levels you would deal with an inlet silencer. High outlet sound power levels you would deal with an outlet silencer. If it's heavy radiated casing noise, then you've got to deal with some kind of acoustic cladding, acoustic jackets. There's a lot of way to mitigate it. You could also alter things in here. You could create damper curves. You could change the density if you need to. You could add accessories like a damper or a silencer to see what the associated pressure drop is and what speed you need to run it at to combat that. And then there are several AMCA publications that I'm going to point you toward. There is AMCA 201, and this discusses the effect of inlet and outlet connections on fan performance. So that really gets into the topic of system effects, which again, Jim Conway from New York Blower is going to be presenting on tomorrow. So that'll be a good one to understand the relationship between a fan and the system it's installed in. AMCA 202 is a good troubleshooting handbook. It talks about how to correct problems in installation. And AMCA 203 talks about field measurements. So if you need to do some kind of a field testing, it's going to be a different setup than the typical lab testing that you do. So also a very helpful tool. And I'm actually, looks like I have a couple more minutes, so I'm going to give you a couple pointers on a couple of the fan types that we looked at. So there are definitely a few boiler manufacturers here. Pressure blowers are pretty common on the boilers and the burners that heat the air that they use. And pressure blowers are not at all material handling fans, but they do generate a ton of pressure at very low airflows. You could tell just based on the wheel construction, these are smaller, narrower blades. There's really no width to handle material. And they're typically made lighter construction. They're riveted in aluminum a lot of the time because they typically need to run at very high pressures and high speeds, and having it lighter helps with that effort. They can be steel, they can be open face, or a few different ways to do it depending on what's needed out of it. But that's the pressure blower, very common. And then a quick note on radial bladed fans. Again, they tend to be less efficient than backward inclined fans. They generate very high amounts of pressure at lower to moderate amounts of airflow. And there are a lot of different styles to think about. So if you get into a material handling application, just know there are different wheels out there depending on how rigorous the application is. And it's going to get a little less efficient with the increase of duty. So if you're dealing with a paddle blade, less efficient, excellent at handling material. You can make it more efficient by adding paddles. You're also taking away from its material handling capability by adding points of hang-up for stranded materials. Similar with the dust handling wheel, this is getting as efficient as you can get, about 65 to 70% for a radial bladed wheel, but now you're curving blades that need to be thinner to be curved. You're adding shrouds, a lot of points of contact for hang-up. So just a quick overview of radial bladed fans. And with that, I'm going to open it up for questions if anybody has any. Thank you guys all for coming.
Hey, regarding that slide that you had on the spark, assuming that you have just clean air, like in this room, are there any significant risks for creating a static electricity because that could potentially become a hazard?
Mm-hmm. Yeah, sparking is another thing to think of separate from mechanical sparking. You do want to think about static electricity, and grounding is one way to deal with it. It's typically something you could order separately is static grounding. And some level of spark resistance, you can at that point probably be looking at something more minimal like buffers as opposed to making the entire airstream out of it. And if you're dealing with FRP, a plastic fan, then it's not ferrous to create sparks, but it can create a static buildup, and so there's graphite impregnation available when you're working with that. Yes?
Sorry, in a fan array application, Is it more energy efficient to run more fans at a lower horsepower or less fans at a higher horsepower?
I would say more fans at a lower horsepower, but
Because that quadratic equation.
exactly.
Yeah.
Right. But then it does depend. If you're running really smaller fans a lot faster, it kind of depends if there's a larger, slower option out there too. Yes.
My name is Walter from Boulogne. I have a very specific question. You mentioned forward and backward curved blades, also together with furnaces. Why do you think that with furnaces the forward curved blades are better than backward curved blades?
Sure. So he's asking about forward curve versus backward incline specific to furnaces. And forward curve, you see a lot of them because of their ability to move the amount of air that's required of them at slower speeds. Because when you're dealing with a backward incline, you're going to have to move it pretty fast to increase the amount of airflow that it can move. They're higher airflow moving fans, but you're going to have to get into the type of materials that you're building the wheel out of. If you're dealing with forward curve, it could hit higher amounts of airflow at proportionately lower speeds. And so you don't have to worry so much about the material D, right? It's better suited to move the amount of air that's needed for those applications at lower speeds, so you don't worry about the maximum safe speed at a hotter temperature.
Thank you.
Sure. Yes?
Hi, I was just wondering, so very early on in the presentation, you showed that table of how changing the speed rotation changes the power generation and the pressure inside the duct. Does that information vary much depending on the actual material that the fan is made of?
Yes. Yeah, so I should have mentioned, with the fan laws, it's really, it goes with the caveat of all else being equal. So there are other changes, for instance, how density affects fan performance. And that kind of comes into the rest of the fan laws. So there are a lot of other fan laws that cover that kind of stuff about what's moving through the airstream? How does that affect the pressure and the airflow? If it's more dense or less dense. So yeah, I forget which AMCA publication it is, but there's something out there that covers the rest of the fan laws to get a lot more in depth than just speed and airflow and pressure and horsepower.
Thank you.
Sure. Anybody else? Thank you very much, everybody.